All right, second half of section 4.4, page 254. All right, just in the way of review, remember that we talked about if you want to identify a vertical asymptote, your vertical asymptote is typically going to be where your denominator is equal to 0 if you have your rational function in its lowest terms. Now, there may be an exception to that, and for AP purposes, that's not an acceptable justification. So we can identify possible vertical asymptotes by setting our denominator equal to 0, but then we do still have to go back for our verification or justification if they ask for that, and take the limit as x approaches that value and make sure that we get a limit that's going to infinity or negative infinity to check that. Then for our horizontal asymptotes, we learned that if you take the limit as x approaches infinity or negative infinity and you get an actual numerical limit, then that limit will be equal to y equals that number as a horizontal asymptote. We also talked about in pre-cal, we had a really great way of helping us find those horizontal asymptotes. We compared the degree of the numerator and denominator, right? So when the degree of the numerator was larger than the degree of the denominator, we didn't have a horizontal asymptote. So that might lead me to an answer of like infinity or negative infinity or does not exist or something like that. If the degree of the numerator was less than the degree of the denominator, then I did have an asymptote. It was y equals 0. And if the degree of the numerator was equal to the degree of the denominator, I did have an asymptote, and it was y equals the leading coefficient of the numerator over the leading coefficient of the denominator. But again, even though that gives me a practical way to find my horizontal asymptotes in terms of justification or verification, I do have to show that the limit as x approaches infinity or negative infinity of my function leads to that value that I'm stating is my horizontal asymptote. So yesterday we also learned in the first half of this lesson some tricks that we could use to find those. And one of the most beneficial tricks was when you're taking the limit of a number divided by a variable that has a positive exponent, that limit when you're approaching infinity or negative infinity, that limit is always going to go to 0. When you have the limit of a number divided by a variable and you're taking the limit as x approaches infinity or negative infinity, that limit always goes to 0. That was a property we saw because the numerator is staying the same and the denominator is getting larger and larger and larger, so the overall fraction gets smaller and smaller and smaller, right? So something else that we learned as a trick yesterday is that if you go through and you divide everything in a rational function, a fractional function, if you divide everything by the highest power of x in the denominator, a lot of times it will create what is left over to just be constants and numbers divided by variables that then I could use those little shortcuts on. So those were some of the tricks and some of the tools that we were utilizing yesterday. Today we want to look at some more troublesome problems, like some that are abnormal, ones that might be more problematic for us, and how we could approach those. Okay, so the first thing that we want to look at in example number 4 is, what if I'm taking the limit as x approaches infinity and I want to do that whole divide everything by the highest power of x in the denominator, but I have a radical in my problem? All right, so if I go through, and in this case, this was the function that they gave me, I could go through and use the idea of setting the denominator equal to 0 to identify my possible vertical asymptotes. I would have to verify that by actually showing that the limit as x approaches that value does give me infinity or negative infinity, so I can do that. But specifically what we're focusing on in this section is how to identify the horizontal asymptotes. So if I go through and I divide everything by the highest power of x in the denominator, I'm going to be dividing by x to the first. That's okay down here in the bottom. Divide everything by x, divide everything by x. I come up here to the top to divide everything by x, and it's a little more troublesome because I'm not really sure how to divide the radical by x. The only way I could divide the radical is if I had a radical. But I could do that. I could rewrite x as the square root of x squared. If I rewrite x as the square root of x squared, now I have a radical divided by a radical. Remember that you can combine that under one single radical, and I could simplify that. So I could say 2x squared divided by x squared is going to give me 2, and 1 over x squared, and now I'm good to go again, right? So I can go through and take the limit. Remember, we have a property that says if you have the limit of a radical, you can take the limit of what's under the radical first and then do your square root or cube root or whatever you have. So I'm going to go through and say the limit of a constant is that constant, and the limit of a number divided by a variable is 0. And then down here, limit of a constant is that constant, and limit of a number divided by a variable is 0. So that gives me square root of 2/3. And if I did my cool little horizontal asymptote test from pre-cal, I would have looked at this and said the degree of my numerator is the square root of x squared, which is x. The degree of my denominator is x, so x to the first and x to the first. Degree of the numerator is same as the degree of the denominator. So my horizontal asymptote should be leading coefficient over leading coefficient. So that'd be square root of 2/3. So I get that. I'm good. And then I look in the back of the book, and it says your horizontal asymptote is not only the square root of 2/3, but it is also a negative square root of 2/3. Square root of 2/3, not square root of 2/3. Square root of 2/3 and negative square root of 2/3. Where's that negative thing coming from? And that's what makes this problem a little bit different. When I go back and I think of the limit as x approaches negative infinity, typically when I divide everything by highest power of x in the numerator and denominator, I don't have to think of it separately as infinity and negative infinity, but because of the radical here, I'm going to need to consider this one separately. If I go back and I take the limit as x approaches a negative infinity of this function, magically a negative appears that did not appear up here. Where in the world did that negative come from? Well, when I replaced x with the square root of x squared, by definition, the square root of x squared is the absolute value of x, and absolute value of x is a piecewise, right? If what's inside that absolute value is greater than 0, I get what I started with, but if what's inside that absolute value is less than 0, I get the opposite of what I started with. So when I inserted the square root of x squared up here, I was working with the absolute value of x. And each of the values that I was putting in for x, since it was approaching a positive infinity, every one of those values would have been greater than 0, so I would have gotten exactly what I started with. But down here, when I replace x with the square root of x squared, which by definition is the absolute value of x, because I'm approaching a negative infinity, every single value that I'm plugging in is less than 0, right? So when the values that I'm working with are less than 0, I'm going to get a negative x. And so that's where that negative comes from. And that's a little abnormal and bizarre. It only shows up in that particular situation. But that's where that second horizontal asymptote is going to come from. All right? Let's look at some other abnormalities, if you want to call them that. Look at example number 5. Example number 5, they asked me to find the limit as x approaches infinity of the square root of x squared plus 1 minus x all over